So last time we looked at this PDE and I wanted to just go over it really quickly again, especially the part where we decompose this into a steady state ODE and a transient PDE. Again, the separation of variables and this solution structure here of separating the actual PDE into two problems, the steady state and the transient, that's a fundamental technique. And so it's important, that we make sure we get it right here. So here, as always, I'm going to ask you to really think about what you're looking at and take a look at the PDE and appreciate the different parts of the PDE, right? So we have the actual PDE inside the domain here. Then we have our boundary conditions these are the physical boundary conditions on the left and right end of the rod. And so here we assume T sub 1 and T sub 2 are not 0. Okay, so we only do this process here if the set of functions, that satisfy the PDE and the boundary conditions form a vector space, then we don't have to do this procedure that I'm about to do here. So in this case, we assume T1 and T2 are not 0, and that the set of functions that do satisfy these boundary conditions do not form a vector space. Finally, we have our initial condition. So this is, when we say initial condition, this is with respect to the T variable, right? So that's our initial condition, which we will actually use as at the final step of the formal solution. So in this case, because the set of functions, if we look at the PDE and boundary conditions and ask the question, do the set of functions that satisfy the PDE and the boundary conditions form a vector space? If T1 and T sub 2 are not 0, which is what we're assuming, then the answer is no, they do not. So now we need to do some math trickery. And there's also, a physical and conceptual reason for this. We write the temperature, the solution we're looking for, U of xt, as having two parts, a steady state U bar of x part solution, plus what we call the transient solution, the transient. And so the transient has two variables. And so for the transient V of xt, we need a proper PDE, which means I need, proper PDE boundary value problem, which means I need a partial differential equation for V, I need boundary conditions for V, and I need an initial condition for V. For U bar, that's a ODE. There's no time variable there. There we just need, the ODE and whatever boundary conditions for the ODE. So, okay, so mathematically, it's not difficult. We're gonna, how do we use this assumption? We're gonna replace U in the PDE and boundary conditions with U bar plus V. So these U's we replace with U bar plus V, and we decompose it. And so when I do that here, here I calculated each side. Partial U partial T is 0 plus partial V partial T. And K, the second partial of U with respect to X, is KU double prime of X, K times the second partial of V with respect to X. And so now, we equate like terms, so here, the partial with respect to V, obviously I equate with this K second partial with respect to V. And everything else we equate to each other.
Dr. Bott,
Yes,
quick question here
Yes,
for U bar double prime equals 0.
Yes.
Does that imply that the form of the solution must always be either a function of x squared or a linear function in x?
The formal solution. What was the question again?
So if U bar double prime of x equals 0, then is that either quadratic or linear in x? Is that the implication there?
Well, it won't be quadratic. It will be linear. It will be linear in x. That's definitely the implication there. And I mean, I guess that's a result of the underlying, fact that the right-hand side is of second order in the space variable. Okay. Of the PDE. Yeah.
I'll talk to an officer, I'm getting something different than that for problem 3, where there's,
Yeah, so we should talk about that separately. Yeah.
okay.
Well, in problem 3, there is an internal heat source.
Okay, so this is
Yeah,
absent heat sources.
Yeah, see, there's no plus Q term here. And so that's a
Right.
great comment. That's a great comment, by the way. Just
Okay.
in general, if I had a plus Q term here, and for us to have steady state, it would have to be only a function of X. So this is a good question, by the way. So then we would put that plus Q term with, so it'd be a negative when you move it over,
Mhm.
with the steady state ODE. And in that case, if we have an internal source of energy, then it's not necessarily true that that term would be linear.
Gotcha. Thank you.
Good
Okay,
question. Good question. Good question. Yeah. So here, no internal heat source. So now we've got the PDE for little v. The PDE here for little v. I've got the ODE for the steady state. And now, I need boundary conditions for the ODE. I need boundary conditions for the PDE and initial condition for the PDE. Again, the math part is not difficult. Again, we just take U bar plus V and replace the U, everywhere the U occurs, we're going to replace that. We're just going to use this assumption. And then we can accordingly, decompose the resulting equations to get our system of the ODE and the PDE. So here, that's what we do for U of 0. We're given that it equals T1, but if I apply the assumption that our solution is, a steady state plus transient, we can now decompose this equation. So here's the part that's a little subtle thing, is we're always working to where we want the PDE, the transient PDE, we want that to form a vector space, the set of functions that satisfy the transient PDE and the transient boundary conditions should form a vector space. So that's why I say here to use a strategic application of the boundary conditions, and that's exactly why we pick V of 0 to be 0. And everything else that's left over, we put onto U bar of 0. Similarly, at the other end, the strategic application of the boundary condition. And finally, so that gives us also the boundary conditions for the steady state problem. So finally now, for the initial condition for the PDE, again, we just go back to the given information and plug in U bar plus V for U, and now solve for little v, right? We want the initial condition for the PDE, so solve for little v. And so this becomes our initial condition. And so now, we can formulate our steady state and transient problem. In this case, that's the steady state. Here, there's no internal source. We can just integrate twice, apply the boundary conditions. You get this type of linear steady state. And then the transient problem is exactly this, heat equation with the trivial Dirichlet boundary conditions. And here, we've got our initial condition here that you can see is explicitly based on the transient, right? So here we need to note the transient solution for this. Of course, when U bar is 0, then, probably your original PDE, the functions that satisfy the PDE and boundary conditions form vector space, you can just do separation of variables directly. So now keep in mind, so now what do we do? So now we do separation of variables here, like you've been doing your homework. Assume V is F times G and blah, blah, blah. We don't say for this transient problem, we don't say, oh, let's break this up into steady state and transient. Because for this transient problem, we know it's set up to where the steady state's trivial. It doesn't have, it's just the set of functions that satisfy the PDE and boundary conditions form a vector space. We can do separation of variables directly. So now we get this solution. Just to remind you here, just this part is a constant. That's the really important thing that I want you to see. Here are variables. There's the x variable and the t variable. This part never changes. The sign, this part never changes. That's always going to be part of any heat equation solution with either homogeneous Dirichlet boundary conditions or steady boundary conditions, where the boundary conditions are like this, you know, like for this u of 0 equals some constant and u bar of L equals some constant. Those are called steady boundary conditions. But of course the partials, you know, on u. So here, this is the only part. This is where, when we talk about data, so sometimes people say, oh, if the data you're putting into the system is smooth or not. So we talk about data, we're specifically talking about this portion right here. So, hold on. Zoom's messing with me. Okay, so yeah, so when we talk about data, look, this function here, F, this is what we're inputting into the system. Really, it's the boundary conditions and this initial condition. So assuming the boundary conditions are fixed, you know, whatever they are here, T1, T2, then this is really what's gonna cause the series to converge or diverge. This is where the convergence divergence is, you know, so this is the coefficient. This is where we talked about if the function is piecewise smooth, then according to the Riemann-Lebesgue lemma, you'll have oscillatory cancellation. And these coefficients will go to 0 fast enough. This exponential term here is going to 0 very fast also. And so that's where the convergence happens. So the data we put in, that's why this data is important. That's why this will affect the convergence, you know, if it's not, as we've talked about it being piecewise smooth. So, and our solution ultimately, you know, is totally dependent on that initial condition and boundary condition. So finally, here's the full solution. We put it together with the transient solution and the steady state solution. Here's the steady state solution in the front. And I say from boundary conditions. So here, you know, all of this information, T1 and T2, all that information was from the boundary condition on the original PDE. And then here, the solution of the transient part, here's that constant I was talking about. I mentioned it's from the initial condition. You can see here's our initial temperature information right there. And then the rest of it is basically from the separation of variables. This part is from when we say U equals F times G, and we solve the time domain problem, and we solve the boundary value problem, the eigenvalue problem, and apply the boundary conditions. So that's where that part's coming from, you know. And then the reason we're able to finally at the end stitch the entire solution together, so I'm able to sum a linear combination and add the two together, that's the vector space theory, that's the superposition that allows us now to cobble together this, you know, formal solution of the PDE, which has been created mathematically to solve the problem, but we don't know if, you know, our creation will live up to the hype. So we have to verify, number one, does it converge? And we know it converges if you know, the initial condition is nice enough. And number two, does it satisfy the heat equation? So here, what we want to show is that this function, which, you know, has this form, whoops, sorry. Zoom is always messing with me. So what we want to show is this function that has a generic form constant times the rest of it that we got from the separation of variables. We want to show in general, because that's what we, you know, when you did separation of variables, this was the product solution where we didn't know what B sub n was. So here, this part should at least satisfy the PDE, because mathematically that's what it was created to do. So what we want when we say that it's a solution, that number one, that we have convergence and the series for these partials also converge, and we want it to satisfy the heat equation. So here we can show that it does. And so I've done the math here, it's not difficult. So here I'm doing the partial of u of this function with respect to t. So there's just this part. When you take the derivative, the derivative of e to the u is u prime e to the u. So here I just copied the e to the u part, I just copied. And now if you look upstairs, here, the derivatives with respect to t. So I just have minus quantity n pi over L squared times k, because the derivative of t is just 1. And so that's what you see here. Minus n pi over L quantity squared times k with the minus sign in front. And now I do an x derivative. So here the only part that's a variable of x is the trigonometric function. So here's my chain rule of taking the derivative of sine of n pi x over L, right? The derivative of sine is cosine n pi x over L times the derivative inside is n pi over L. And then we do one more spatial derivative. So here's another derivative. So the derivative of cosine is negative sine, there's the minus, and then times the derivative of the inside. So you get another copy of n pi over L. So here you have n pi over L squared. And now if you look, so now we're comparing this and this equation. And you'll see they're almost identical. The only thing is the k is different. So if I multiply both sides of the equation down here, the second partial of u with respect to x, if I multiply both sides by k, then these two will be equal. So that's what we call proof is in the pudding, right? We proved it. We did the partials. I'm showing you that they're literally the same if you multiply the second partial of u with respect to x by k. So that's progress, folks. So now we know that the thing we created mathematically and in theory, we know it actually works. So let me talk about the convergence. I didn't talk about convergence yet. So in general, if you look at the partials of u and x, they have this kind of generic form where, maybe we'll go back, where you have, there's an exponential part, there's this n squared part, there's a trig function, right? There's the trig function, there's like the n squared part, there's the exponential part, and then finally there's this b sub n coefficient in the front. So, I'm going to analyze it generically. So I want to look at a series that has that form. Here's the b sub n, here's the n squared, here's the trig function part, here's the exponential part with the t variable in there. So remember, t is time, and we're assuming t is greater than 0 here. Okay. So now I'm going to do some analysis, folks. I'm going to do some math involving inequalities and whatnot, because the name of the game now is we're just doing some calc 2. I'd like to bound the series of absolute values by a series that converges. Something here that converges, that we can show converges. Maybe using a ratio test. And so this is a question mark. That's what I want to do. So now we're going to do a series of inequalities and math trickeries and manipulations and gyrations for the sake of getting this inequality. And you say, why are you doing all this? Because it works. At the end of the day, why do anything, right? Because it works. So here we go. And some of these moves are like some nice basic analysis moves that if you're going to take analysis, you should like keep these in mind. So here our sequence, our series, n, the index is n is greater than or equal to 1. Okay. So what you do now is this is a nice numerical analysis trick. You multiply both sides by n. because n is greater than or equal to 1, so n's a non-negative number, I can multiply both sides by n without affecting the direction of the inequality. I get n squared is greater than n, which is awesome and groovy. Then multiply both sides by c times t. C is assumed to be a positive constant, and t is also positive, it's time. So here, no problem, the inequality doesn't change its direction. Now exponentiate both sides. As you know, the exponential function is an increasing function. So what does that mean? That means if a is less than b, then e to the a will be less than e to the b. So here, you have, or if b is greater than a, then e to the b will be greater than e to the a. So it's an increasing function. So here, if ct times n is less than ct times n squared, then e to the ct times n will be less than e to the ct times n squared, because it's an increasing function. Finally, if you look in our form, I have a minus sign here, so I'm going to take a reciprocal. So we take a reciprocal, as you remember, the reciprocal function is decreasing, so here we reverse the direction of the inequality. So finally get e to the minus ctn squared is less than or equal to e to the minus ctn. And that's progress because I got rid of the n squared. Here, I have this n squared, which is not so nice. And now I've managed to bound it. And here I just have an n, which is nicer. I'll show you why. It's nicer analytically to work with. It goes to 0, not as fast as minus e to the minus ctn squared. So here, let's do our analysis shenanigans now, folks. Remember your theory. Remember your series, from Calc 2 here. If this series converges, the series of the absolute values of the terms, then we know the original series will be absolutely convergent. That's the definition of absolutely convergent. Okay, so if I can show this converges, then we've got absolute convergence of the original. And so then we'll know both the partial with respect to t and x both converge. Okay, so finally here, throw on some absolute values and just do some, basic algebra here. I've got absolute value of this constant right here. N squared is non-negative, so absolute value of n squared is just n squared. The absolute value of sine is less than or equal to 1. And so that's where this 1 is coming from. And we just showed e to the minus ctn squared is less than or equal to e to the minus ctn. And so now, here's an if here, if there exists some positive constant m, such that all of the b sub n tildes is less than or equal to m, then I can further bound, this series here. So this is less than this, and now I'm saying this will be less than this thing here if this term, absolute value of b sub n, is less than m. And now I claim, that this series here, you can use a ratio test, or actually I think it might even be a geoseries or something like that. You can use a ratio test to show that series converges, which I'll do in the next set of slides here. And actually, I think I do it with a geoseries. Either way, you can show it converges. And so we'll be able to show that the original series up here is absolutely convergent. And so we'll get the partials are converging, and we verified that it satisfied the heat equation. So then we'll basically be in business. So this is to be continued on the next set of slides. So let me switch over. And first, show Zoom who's in charge here. You're not the boss of me, Zoom. Okay, so, and now the conclusion of the convergence discussion. Okay, so here, this is just a reminder, this slide, I just wanted to always kind of remind you, with this material, it really helps to, at least initially, not even initially, all the time, to go over the fundamentals and remind yourself how this goes. So with the separation of variables, we get the time domain and boundary value problems, and then use our superposition and all our math trickery here to create this formal solution. And so I showed you that we could bound it with this function of this form. You can go all the way to infinity, actually, with a function of this form. With a constant e to the, we had a constant, I just called it c, then we had n squared kt, and then we bounded this, right? So this still has the n squared. So on the next slide, I'll show you the bound we actually did. This still has the n squared. Remember, we then further bound this using our math trickery, which I've repeated here. This basic fundament, the basic trick is right here. This is the math trickery that makes it all work. And then you multiply both sides by a constant, then you exponentiate, then you take the reciprocal, right? And then now I can bound each part. You can, I assume that the B sub n had a constant that you can bound it with. And so of course that depends on the initial data, right? So here, one thing I've already done, so sorry, I'll get back to that. One thing I've done is, remember there's a B sub n term, and I'm making assumption that B sub n is less than capital M. Now think about what B sub n is. It's the integral from 0 to L of f of x times sine. So that integral is if it's not well behaved, remember sine's a bounded function. So if that integral is going to blow up, it's going to be because of the f of x function, the initial condition. And now if we require that initial condition doesn't have any infinite discontinuities, its derivative doesn't have any infinite discontinuities, it's piecewise smooth, then that B sub n is going to be very well behaved and bounded. Okay, so let me back this up a second here. And so here's the end of the argument. So here we had bounded our original solution, the series of the absolute values of our terms. We bounded it with this term, with the n squared up here. And now using the math, above, we've now bounded it with this term where you no longer have an n squared. I don't know if I should have a square on the constant, but the constant part really doesn't matter. All that matters really is the n. And so here, yes, I don't know if I'm missing this square right here. Should be right here, right? So I'll put that in later. So many moving parts. Right? Does that look better? Yeah, that looks good. So yeah, I forgot a little square there, but just on the constant. So it doesn't really matter, the constant. Right here, there should be a square. So if you look at this series now, this is a geoseries. So this is a series of the form sigma A times R to the n, where this whole part is R and this part is M. And so this here, the R part is e to the minus pi L kt. And pi L kt is greater than 0. So you think about the graph of, e to the minus x, if x is greater than 0. this part, the R from our geoseries is actually less than 1. And so we have a convergent geoseries. And so this is the sum, which I'm sure is wrong because I'm missing the square up here, right? So I'll figure out the sum and fix that typo. But the bottom line is it converges. And so our original form here, this thing, will be absolutely convergent as long as absolute value of B sub n can be bounded. And that depends on the initial condition, So if we want B sub n to be well behaved, we need the initial condition, the initial temperature, f of x. We need that to be piecewise smooth. So every other part of it behaves nicely. Yes, go ahead.
Sorry, didn't mean to interrupt.
No, you're fine. Go ahead.
Why does pi L squared KT strictly greater than 0? Why don't we get greater than or equal to 0? Because T can take on like our initial condition 0.
Well, when T is equal to 0, this part disappears. This part disappears when T is equal to 0. Like this part disappears. And you're just looking at the Fourier series representation of f of x on the boundary. When T is equal to 0, it's just a Fourier series.
Yes, okay.
So, and the Fourier series theory, we know from Dirichlet's theorem, if B sub n is well behaved, then that'll converge.
Okay, cool.
Alana.
Why are we doing a direct comparison test here instead of the Weierstrass M test?
I just mean it's a direct comparison in the sense that I'm comparing this series. I'm saying this is less than or equal to, I'm just using the result that if we know that this series converges, that's supposed to be an infinity, then we know the original series converges. I'm using that result.
Mm-hmm.
And that result you can prove using a direct comparison test. So at the end here, really all I'm trying to say is because I know the series of absolute value of all this junk converges, we have a theorem from Calc 2 that says the original series converges absolutely. And one of the ways you can prove that theorem is using direct comparison tests. So that's kind of why I worded it that way.
Okay. So
because I taught Calc 2 one time too many.
Okay. So if we did this without taking the absolute value of the series first, then it would be converging uniformly.
It'd be very, very, very difficult to do this without taking the absolute value first because of the oscillating term is very hard to work with analytically.
Okay.
So one of the tricks here to not having to deal with the oscillating term is when we take the absolute value, we can then bound this with 1 and we make a complicated function disappear. So that's one of the analytic tricks here, is to look at the absolute value of this thing and then bound it and get rid of as many complicated terms as we can.
Okay. Cool. Thank
you. And so, once we have this result once, it's not like I'm going to ask you to prove this, so this is for us to now mathematically believe that, okay, this formal solution we created, it does converge. At least we can use our, Calc 2 sequence and series stuff to show that it converges. And so, yeah, here's my, I keep, trying to connect it back to the initial data. So here it comes back to if B sub n is well behaved. And so, we did this theory for the Fourier series about piecewise smooth functions. And that's exactly, comes back to what does f of x look like? So when we say initial data, I'm talking about the initial condition f of x that we put in, when t equals 0. This is regarding the initial condition. So if it's piecewise smooth, or if it's, more than piecewise smooth, then of course nice things happen. And typically we don't want to look at the problem where we don't have nice data. We're asking for trouble. So yeah, so in general, without getting too math technical every time, typically if we start with reasonable initial data, f of x, then more often than not, B sub n will be bounded, and typically this formal solution will work most of the time for nice data. So just as a general generic statement. So Alon, did you have another question, or did I forget to unraise your hand?
Yeah, one quick question. So
Yeah, go ahead.
on the last slide, it had
Yeah, go ahead.
just like regular BN, and on the slide before, or the last set of slides, I guess, we had BN tilde. Is it?
Yeah.
Are they the same?
I was just kind of using BN tilde very generically, because on the last set of slides, I wasn't necessarily looking at something that was a solution to a heat equation. It was just like a BN tilde that could be anything.
Okay.
And then now on these set of slides, I switched over specifically to the solution to the heat equation. And now this B sub n is, like the formula using the orthogonal formula, whatever B sub n is for a Fourier sine series.
Okay, cool. Thanks.
Thank you for that clarification question. That's a good question. So I want to do a quick example, just because we saw all of the theory, but let's do an example with numbers and blah blah, and analyze the solution and think about it a little bit now that we know how to solve a solution, a PDE. So here's a PDE boundary value problem with the initial condition. Here, so at this point, I don't expect you to do separation of variables every single time now. At this point, we know the solution, we know the formula for it. Now I want you to be able to look at the PDE and just start to automatically analyze what kind of solution it has. Like from seeing these boundary conditions, I know here, okay, I don't need to break this up into a steady state and transient. Here I can solve the PDE directly. Here I know the solution will be like a Fourier sine series, and we know that the form of the solution will look like this. At this point, since we've done all of that work, I don't need to repeat all of that work. So I made you do separation of variables on a homework, So now if it says you don't need to show all the steps of separation of variables, it means you can assume all these things. Like we know this because we've done this now. So here I can skip directly to this step that, based on our theory and based on the fact that one important subtle point, okay, is here because of these boundary conditions, the transient solution is trivial. Here, the set of functions that satisfy the PDE up here and the boundary conditions forms a vector space. So I can just go right directly to the formal solution of the PDE. The transient solution here is trivial. Okay. And then we know from our orthogonality theory and stuff that B sub n has to have this formula. So really the only work to do now when we're solving a PDE, for example, in this PDE, is to figure out this integral. I just need to figure out this integral and then stick it into the formal solution. Figure out what the integral is and then put B sub n in here. And then I've got my formal solution, which we know if the initial data is nice enough, we know it'll converge, it'll satisfy the heat equation, blah, blah, blah. So here I do the integral, the integration is not difficult. You get one of these deals where you get a cosine like n pi type of a thing, and you get one of these deals where it's like -1 to the n -1 or something like that. And so when it's even, it's 0, and it doubles up. It's not a -2. So this is what I've written here is not quite right, but it's one of those deals. When it's even, it's 0. I'll let you do the integral. It's not difficult, right? Here, this is just a constant. You can just integrate it directly. No tricks necessary. If it's even, the terms cancel out. If they're odd, the terms double up. Okay, and so don't forget there's 100 here, which you pull out. 2 times 100 is 200. And when n is odd, you can show that things double up. So the 200 times 2 is 400. And the n pi is from the integration. because the antiderivative sine n pi x over L is L over n pi cosine n pi x over L, right? And so that's why the L's cancel. Okay, so this is all math you've done so many times in the homework, a million times, okay, that even you're sick of it. So now we're going to do the usual trick. I'm going to replace n with 2p minus 1. Again, this is a trick you've done in your homework a couple of times now, because here only the odd values of n are relevant. The even values of n give us a 0 term. So I'm going to replace this n right here with 2p minus 1. I'm going to replace this n up here with 2p minus 1. I'm going to replace this n all with 2p minus 1. And then I'm going to start the series. I'm going to start that at p equal to 1. Right? Just converting it to a nice series representation. Oh, here, by the way, notice here that the absolute value of b sub n in this case, you know, because we had a really, really nice initial condition, is bounded. Because it's equal to a constant, right? And n gets bigger, so this whole thing goes to 0. So we can say they're all less than the first one, 400 over pi, because as n gets larger and larger, 400 over n pi goes to 0. So here we know the solution will be absolutely convergent from the work done before. We know the solution will satisfy the heat equation from the work done before. And we know that when t is equal to 0, so when t equals 0, we get a Fourier sine series. So when t equal to 0, the exponential term disappears. We get a Fourier sine series. So hold on, let me replace this t right here with a 0. When t equals 0, we get a Fourier sine series, and we know here the function 100, that's piecewise smooth, so this thing converges, so this thing will equal f of x. And so when t equals 0, this thing will equal our initial condition f of x. And so for all intents and purposes, we've definitely found one solution to this heat equation. I say a solution because we haven't proved uniqueness. You're like, just when we got out of the woods? No. It's entirely possible that there's another solution out there that we could find by using some other technique, not separation of variables. So, I mean, I think just so we can sleep at night, it does turn out that the solution is unique. And so maybe I'll put a homework problem about that later on. But yeah, so yeah, here we've actually solved, here's a bona fide solution to a PDE, and you understand every part of it. You understand the Fourier sine series theory in the background. You understand the superposition. You understand the separation of variables that we use to solve the time domain problem and the boundary variable problem. You understand the convergence analysis of the series. And you've also verified that it does, in fact, solve the heat equation. So here I do some graphs. And so now that we have the solution, we can let's approximate the temperature and blah, 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 play around with it a little bit, do some numerical experiments. So here I assume L is 10 centimeters. I assume K is 1 centimeters per second, which apparently is the diffusivity for copper. I don't know. I got these numbers from Harvey. And here I picked T to be 0.35. I tried to look up diffusivity numbers on the old Googles, and I don't know what the hell I'm doing. I'm not a very good applied scientist. Math, okay. Actual useful stuff in the real world, not so much. So here, so I wanted to graph it at a very small t values, t slightly larger than 0. Okay, so this is at 0.35 seconds, and I use the first 8 terms. Obviously, I can't use all the terms. So here I'm using this approximation where I've plugged in 0.35 for t. Remember, the exponential component is the only place the t variable shows up. So here, this thing on the right-hand side is a function of x only. X is the only variable on both sides. And so now I'm going to graph it where x goes, from 0 to L. So here's the initial temperature starting out at T equal to 0. That's the initial temperature. As soon as time starts, the ends cool off very quickly. Why is that? Think about the boundary condition. Here we're forcing, we say U of 0 comma T equals 0. The left end for all time has to be a fixed temperature of 0. So it's connected, it's attached to something that's 0 degrees. The boundary condition on the right end also is U of L comma T equals 0. So as soon as time starts, the temperature at the ends of the rods are forced down immediately to 0 because of the boundary condition. So hold on, hold your horses if you have horses. So here, look at the boundary condition here, right here. Look at this cooling boundary condition. So the math is doing what the PDE, what the equations are telling it to do. It starts with an initial temperature of 100, but the minute time starts, the boundary condition kicks in and the ends are cooled to 0. Here, we have, yeah, go ahead, Evan.
So in general, it doesn't matter if the initial condition satisfies the boundary conditions, because at any time past T equals 0, those boundary conditions can be satisfied, right?
Yeah.
Okay.
And there's a great question to ask, is the solution continuous across T to 0? Is the limit Ux T as T goes to 0 equal to, Ux of 0? So that's a compelling analytic question that we will talk about later. And it turns out in general, for nice initial data, it actually is continuous across the T domain somehow as well. A little mind-blowing.
Okay, but in general, we don't have to worry about our boundary
No, in
conditions.
general, we don't necessarily assume that.
Okay.
Yeah, a good question. So here, some things to notice is that here, T goes to 0 as U goes to 0 as T goes to infinity. Like if you look, even at the generic solution, not even this specific solution, they all have this exponential term where it's e to the minus some positive constant times T. So as you send T to infinity, this part of it always goes to 0. So here, we can observe that based on that decaying exponential term, T will go to 0 as T goes to infinity. And so what we can do for approximation, so here what I want to show you what's called the first Fourier mode approximation. So here now we're doing some numerical analysis. So here we want to actually maybe take the solution and try to do some math with it, okay? So here what we're going to do is, because the terms are decaying to 0, we're going to use the slowest decaying term. So think about it, compare e to the minus t with e to the minus 2t with e to the minus 3t. E to the minus t goes to 0 the slowest. E to the minus 2t goes even faster. Here, the more terms you use on your Fourier series, those exponential terms in the top, they're decaying even faster. So here, for when n is 1, which is the slowest decaying term, we can use what's called the first Fourier mode approximation of the temperature, which is U of xt equals, and here I've got the very first term, where this exponential term is going to 0, but it's going to 0 slower than e to the minus, 2 pi over L squared KT, for example, or e to the minus 3 pi over L squared KT. They're all going to 0, but this goes to 0, the slowest compared to those. So this is our slowest decaying term. The second slowest decaying term would be when n is 2, or the second term. I don't want to assume, you might have a Fourier series where just the odd terms survived or whatever. So yeah, the first term of the Fourier series would be the slowest decaying term. The first two terms would be the slowest and the second slowest. And so we can use this. This is an easier function to work with in terms of plugging in numbers. And so we can use this for long-term temperature prediction. So what do I mean by long-term? I mean, T is big. Why? When T is large, these exponential terms get small. The higher degree exponential terms get really small. So for large time, we make the assumption that the slowest decaying term is basically dominating the series solution. Because the more, for large time, the bigger T gets, the closer e to the minus T goes to 0, but the higher powered e to the minus T terms, like e to the minus 2T, e to the minus 2T, those terms go to 0 even faster. So this slowest decaying term is kind of dominating. Oh my goodness, I'm 2 minutes over. Sweet sassy frassy. My bad, y'all. That's all I wanted to say. So in this case, we can just approximate the function with a real bona fide function here that's simple and easy to work with. There's your x variable, there's your t variable, and then we can do fun stuff like graph it, because what else do we do when we have stuff like that? So I'll pick it up right back here next time, and I apologize, but we're pretty much caught up. And yeah, thanks for your time, everybody.